Hi, everyone. I'm Richard, a PhD student from University of California, Berkeley, and today I'm going to talk about how circuit board design tools can more meaningfully support design. But first, since I assume not everyone here lives and breathes electronics, let's start with a motivating scenario. So let's say a maker wants to build something. Well, fortunately, 3D modeling and 3D printing are both widely approachable technologies, so mechanical parts like enclosures aren't really a problem. And many modern devices, especially interactive ones, are built around electronics, but thanks to the rise of plug-and-play kits like .NET Gadgeteer or beginner-friendly development platforms like Arduino, building simple prototypes also isn't a problem. What is a problem, however, is getting beyond the curated gardens of simple prototyping. If you can't find what you need in a prototyping-friendly part, or the fragile mess of breadboard wires is unacceptable, then your next step is to design and build a printed circuit board. And many tools exist for printed circuit board design today, such as Eagle, Altium, and KiCad, and all these share the same basic design paradigm. Users start in graphical schematic capture, like you see there, where they interactively add and wire up abstract representations of electronic components. The circuit can then be opened in a board layout tool, where they place physical representations of those components and route conductive traces between them. And given the usability engineering put into these tools over the years, learning the interfaces generally isn't the problem. Rather, it's what the tools don't do. Users must understand circuit design and all its intricacies, like checking for maximum ratings and compatibility. And the thing is, graphical schematic capture actually dates back to the 1980s as an improvement over the then dominant technique of entering lists of parts and their connections, like that example over there. However, today's world is very different, characterized by massive increases in computational power, expectation of more automation, and the need to serve non-professional users. That being said, there's been some recent work on improving electronics design tools, for example, circuit synthesis from resource requirements with embedded design generation, and using behavioral level design to build hardware with trigger action circuits. But these systems mainly target designers, and really, with the exception of a workshop study on novices, we don't know much about how people design electronics today. Are we sure we're building the right thing, and will it scale beyond novices? So, I think there's a lot we can learn by examining current practices. And for designers of future systems, knowing what works, what doesn't, allows us not to repeat the same mistakes or waste time solving non-problems. So in the rest of this talk, I'll go over the methodology and results of our study into current practices. And armed with our primary finding that the bulk of the creative work happens in system architecture, outside tools, we then propose a concept for tools that work at this higher level of abstraction. From that, we create a click-through mockup, which we use to elicit feedback from our initial participants. There's several ways to approach such a study, but given the lack of existing work, we opt for breadth rather than depth. Therefore, we ran a semi-structured interview study examining design practices from idea to final device. We started by asking for an overview of the high-level design steps in this flow, then dove into detail about each step, including tools used and pain points. This wide scope allows us to not only learn about board design practices, but also look for areas underserved by current tools. Overall, we interviewed 15 participants with experience levels ranging from beginners, building LED boards, to industry professionals working on power converters and consumer electronics. Interviews averaged 90 minutes. We then conducted open coding passes over to transcriptions and ended with codes primarily organized around motivations and methodology. From these, we looked for themes with design implications for tools. And while everyone's design process varied, there were much similarities in the overarching steps. From this, we were able to construct a superset flow. And this process starts with ideas and specifications, which could be anywhere between user stories like, this LED should blink when the button is pressed, and technical requirements for system interoperability. However, these requirements, and generally any step in the flow, often were revised later as designers learned more. Next would be refinement into a system architecture, often represented as a block diagram. The goal here is to map out an implementation for the idea, figuring out the high-level technical details of how to build it. These blocks could either be high-level, like microcontroller or LED, or low level, specifying sub-circuit designs and part numbers for major components, or often a mix of both. And as such, this free-form nature was the important aspect, and these diagrams were typically drawn with pen and paper or graphic software. Prototyping often follows, with the goal being to validate and iterate. Hobby designers might wire up circuits by hand, while industry engineers might iterate on circuit boards. Boards were built according to the current dominant methodology of schematic capture, followed by layout. In schematic capture, concerns were very low level. Mentions of layout and readability were basically as common as circuit design and functionality. Manual transcription was a common process here, such as from reference schematics. And board layout follows, but since this talk revolves around circuit design, I'll leave the details for the paper. One unexpected but crucial finding is that parts are selected at various points throughout this design process. Major ones like chips could be determined during system architecting. Supporting components would sometimes be specified during schematic capture, and generic passive components might not be finalized until component ordering. Well, at the end of the day, all components must be fully specified. This is a good indicator of which parts are important. Overall, the most important takeaway here is that significant design work happens outside the PCB tools, often on pen and paper or with parts catalogs. And as far as circuit design goes, once you get into schematic capture, a large chunk of it actually ends up being data entry and transcription, where there's much less creative freedom. Basically, this data suggests that schematic capture is a pain point. There's a lot of manual and non-creative work. So, how can we rethink circuit entry? The system architecture level of design seems to be a good place to start. Participants generally enjoyed this stage, and the block diagrams capture design intent without getting too mirrored and tedious implementation details. Here's an example of such a diagram for a data logger device, modeled off the abstractions our users described. The idea is that a microcontroller records temperature data to a micro SD card, and a step-down voltage regulator powers these parts from an external supply. One insight is that both the system architecture and schematic are block diagrams, and so we can support this higher level of design in a familiar interface. In fact, some current tools do take a step in this direction with hierarchy blocks, where a subcircuit can be placed as a block or component. The main difference, though, is support for ambiguity. Architecture diagrams specify only what the designer cares about, which may not be a complete circuit needed to build a board. For example, we asked for a step-down regulator in our system architecture here, but we didn't specify a particular part or even a topology, which are all choices necessary for a complete schematic. In this example, I've chosen a linear regulator, but it would also be reasonable to have a buck converter. And to build boards from this level of design, what we need is a solver that can intelligently choose between alternatives in this design space. However, the intelligently part requires a model of electronics to ensure a correct circuit, such as obeying maximum part ratings. For example, if we decided to use that linear regulator there, its inefficiency would lead to excess waste heat and result in a very toasty component. But if we use the switching buck converter, its higher efficiency makes thermals much less of a problem. And once we have settled on a topology and parts, getting a schematic out is just a matter of dropping in its subcircuit. Yet, there are also subtleties in getting this correct. While the reference circuit structure for buck converters is well known, choosing components is much more involved. For example, TI has that application note right there about sizing capacitors and inductors. The insight here is that equations can be written in a programming language and executable, so this component sizing process can be automated. For example, the inductance equation, shown right there, can basically be expressed as a function of the input and output voltages. But since we're using a programming language, we might as well also instantiate the components and their connectivity here too. In fact, this hardware construction language approach is common in chip design, but for us, it's a potential alternative to block diagrams. So to recap, the idea here is basically to allow users to specify design at the system architecture level. And the solver would then choose a suitable implementation for each high-level block, for example, selecting the buck converter for the step-down regulator. And this implementation could then be instantiated by a generator that encapsulates the intricacies of circuit design. But these concepts are just, well, concepts. There's still a lot of uncertainty. Is this abstraction useful? Is it sufficiently powerful? And does it address real pain points? So we ran a set of follow-up interviews to pitch this idea to users and get feedback. We built a click-through mockup of a design flow through the data logger design that we've been using as a running example. These add a degree of concreteness and familiarity to an otherwise abstract proposal. These mockups started with an empty canvas. Then we showed adding one part interactively. And then we fast-forwarded to the system architecture diagram that you've seen already. The system would then solve this design by choosing concrete implementations for the high-level blocks, like we did for a step-down converter. And at this point, the design is functionally equivalent to a full schematic, theoretically exportable to a layout tool. In the interface, the right pane shows details of the selected block, including parameters to convey the parts model, and a listing of refinement types to indicate the solution space. We also walk users through the hardware construction language. We started with the same data logger design as a conceptual bridge, then moved into this buck converter example previously discussed. We asked open-ended questions about advantages, disadvantages, and applicability for each interface, compared with both each other and mainstream tools. 10 of the 15 participants from the initial round of interviews returned for this follow-up study. Interviews averaged 46 minutes, and we used the same open coding procedure for analysis. Overall, the reactions were positive. One main benefit of our proposed approach was much tighter integration. This included integration of parts data, which could enable accurate circuit correctness checks. This would automate a currently manual process that was tedious and sometimes error-prone. Being able to select parts in the same design interface was also convenient, rather than flipping between multiple websites and tools. However, participants also noted that the system heavily relies on libraries, which has potential drawbacks. One issue was trust in correctness. Participants had various criteria to infer the quality of third-party libraries, such as reputation of the author. They also talked about post-generation verification, which varied from connectivity spot checks to confirming datasheet specs. One insight was a comparison of block diagram interfaces and hardware construction languages. While all participants seemed to understand the language approach and its power for parameterized or repetitive designs, it was seen as less useful for more straightforward or connectivity-driven designs. Learning curve was a frequently mentioned disadvantage, and some just preferred a visual schematic. Finally, an interesting but unexpected discussion on interactions arose from the question about acceptable solver runtimes. There were two broad groups here, with an equal number of participants in each. The first group was fine with batch runtimes, where the solver could take minutes to hours. Tools would be faster than manual processes, or churn away in the background, perhaps even overnight. The second group wanted interactive runtimes, where solver operations would complete in seconds. One idea was a modified version of the mockup flow, which could solve selective subsets of the design. Overall, the mockups indicate that the idea is definitely promising. However, while we tried to maintain an internal consistency and realism in our mockup flow, it's no substitute for having the real system. So our logical next step would be to implement the system, run user studies, and hopefully learn more about effective design strategies. It's also important to note that these results are not necessarily limited to electronics. High-level design with support for ambiguity could also be used in mechanical CAD. One might, for example, design an enclosure like that with a cutout point for a push-button switch. And the exact geometry of the cutout would depend on the switch that is ultimately selected. Furthermore, the enclosure design itself can be parameterized using generators, instantiating the same basic pattern in many sizes. In summary, we observed that much of the creative work in current electronics design practices happens outside board design tools. Our main design insight, then, is that system architecture level of design with support for ambiguity. Parse modeling and generator languages are potential mechanisms to bridge this to a fully solved schematic equivalent circuit. We would like to thank all our participants and funders, and we hope that our findings will lay the foundation for a new generation of tools that enables designers to work more efficiently and effectively.
Okay, so time for a few questions before we go into the coffee break.
Thank you. Very cool talk. Debugging a circuit that you've built is very hard, but perhaps much, much harder is debugging a circuit that someone else built, right? So I think were you to build this tool, you might run into an issue, similar to if you were doing like the autocomplete system we saw before, where if it works great, if it doesn't, now you have this problem of learning what were the actual elements that were instantiated here, how do they interact, and where do the issues arise. But one thing that I've noticed that's interesting is in this concept of a solver, you sort of already put thought into where these issues might occur, what sort of gotchas and gimmies I need to pay attention to. Is there any way that you might be able to organize or highlight to the user when things go wrong, which of these gotchas or gimmies might be the relevant thing that they should learn?
I see. So let me think about this for a moment. I think our idea here is the goal at least, is to have a sufficient electronics model where in most cases you would not be able to mess up, right? Like it would model things like absolute maximum voltages, maximum currents, which are probably the most common issues. Now, of course, there are higher level issues like, RF interference or possibly even thermals or like high frequency issues. Those are hard problems. Maybe the solution is just we'll incrementally play whack-a-mole with those as people encounter those issues and extend our models. But yeah, debugging is hard.
More questions? Nope. Okay. Well, let's thank our speakers and Richard once more. After the coffee break, there's still one more session for today.